This video focuses on the remainder theorem and synthetic division. We're going to show you with an example how to find that remainder and what does that mean for its polynomial. So here's the remainder theorem. You don't need to write this down, you'll be able to practice it. When you divide a polynomial by that factor x minus c, and if you get a remainder out, what that remainder is a constant. And this is our little r, our remainder. This piece is our factor, and then after we use synthetic division, this is what we get, the q of x. When you evaluate the function for its remainder, so this would be our c, you get a point on the graph. We'll show you that with the example. So again, you didn't have to write this down. I just wanted to talk through it a little bit, the remainder theorem. So here's an example. What is the remainder of this if we say our polynomial is x cubed plus 5x squared plus 5x minus 2, and we want to divide it by x plus 2. So we're seeing, can we divide the blue and the red polynomials together to factor completely? So we start with our factor x plus 2. We set it equal to 0, and we're going to put negative 2 out in front of our synthetic division box. I've set up my placeholders. My 1 is my constant for x cubed, my 5 is my x squared constant, my 5 is my x coefficient, and then my negative 2 is my constant. Now we're going to do our synthetic division. Bring down the first term 1. Multiply 1 and negative 2 together, and we get negative 2. Add the columns, 5 plus negative 2 is 3. Multiply negative 2 times 3 is negative 6. Add the column, 5 plus negative 6 is negative 1. Multiply negative 2 times negative 1 is positive 2. Add the column. Negative 2 plus 2 is 0. We want to have that remainder be 0. What that means then is this polynomial in the blue is factorable by the one in the red. So the remainder is 0. It is factorable. So I'm going to drop the polynomial by a degree, since this was x cubed. We're dropping it to x squared, x constant remainder. So we say this polynomial is factorable. P of x equals, I'm going to take out an x plus 2. That was my factor. And what I'm left with is 1x squared, or x squared, plus 3x minus 1. If I were to FOIL this purple and blue back together, I would get this original red polynomial. If I wanted to try and continue factoring this purple function here, which is not, to find 2 more zeros of the function. So I factored out the blue from the red function, and now what I'm left with is the purple one. Here's a second example. Use synthetic division to find f of 3. We want to evaluate the function. So essentially what we're doing is we're dividing by x minus 3 with synthetic division. So here's our red function, and we're dividing it by x minus 3. So we set this equal to 0, and we solve for x. So our k is 3. Set up our placeholders. 2, negative 15, negative 10. Oh, I made a mistake. Our x cubed term is nothing. There isn't an x cubed term. Our x squared is negative 15. Our x term is negative 10, and our constant is positive 5. So bring down the 2. Multiply 2 times 3 is 6. Add the column, 0 plus 6 is 6. Multiply, 6 times 3 is 18. Add the column, negative 15 plus 18 is 3. Multiply, 3 times 3 is 9. Add the column, negative 10 plus 9 is negative 1. Multiply, we get negative 3. Add the column, and we get 2. This time, we have a remainder. So that means that this blue polynomial is not factorable. It gave us a remainder. So we could not take the blue polynomial and divide it with the red polynomial and get something that factors out nicely. But we do get an ordered pair. We wanted to find out what is, if this is my domain, my evaluation, what is f of 3? What we get out is our range, our output. So we say this is a point on the graph, f of 3 is 2. Or, as an ordered pair, 3 and then 2. So if you wanted to take the time to graph this red polynomial, you would get an ordered pair, 3, 2, that's on the graph. So that's one of the important things of synthetic division. I can find ordered pairs on the polynomial.